If you want to learn programming and working on projects with STM32 microcontrollers, the first step is to make sure you can turn an LED on and off using these microcontrollers, right? Essentially, creating a blinking LED with an STM32 microcontroller is the first project you should complete. By successfully making a blinking LED, you achieve a major milestone in learning STM32 microcontrollers. This is because it confirms that everything is working properly. The compiler is correct, the programmer is functioning, the programmer's driver software is working, the connection between the programmer and microcontroller is correct, the microcontroller is correctly powered, and all the initial settings like clock frequency are all set correctly. Now, imagine if your first project was a complex one and it didn't work for some unknown reason. You wouldn't be able to pinpoint the issue, right? It could be a problem with the programmer, compiler, or connections, which may not even relate to the project itself. So accomplishing this first step is a huge success. Once you have done this, all you need to do is to learn additional configurations and improve your skills to reach a professional level. In this video, I'm here to help you complete your very first project with STM32 microcontrollers, and by the end, you'll learn all the essential steps for setting up, programming, and using STM32 microcontrollers. Stick with me throughout the video and watch carefully to the end. STM32 microcontrollers are among the best options for many of our projects. These microcontrollers include a 32-bit processor, making programming much easier. They are produced by ST Microelectronics and use an advanced ARM architecture. Okay, let's pause for a second. You probably know me by now, and you are aware that I'm not a fan of getting into irrelevant details like who makes the chip or its internal architecture. So let's skip that useless stuff and get right into the point. But before anything, let's check out a few STM32 microcontrollers and get familiar with them, then we will move on. These ICs here are a few examples of STM32 microcontrollers I have in my workshop right now. Let me show you some of them. For example, this one is STM32F030F4P6. I hope you can see the part number on the IC. And also this one is STM32 103RET6. And this one is STM32F030K6T6. Each of them has different capabilities and specifications, but I'm not going to get into those details right now. As you can see, the microcontrollers come in SMD packages and there are no deep package versions available, so you can't directly use them on a breadboard. However, you can use development boards like the Discovery or Nucleo boards. There are also smaller educational boards like Blue Pill boards available on the market, but still these boards don't fully satisfy me in the term of teaching because they can give the impression that there is something special inside these boards, even though there is really nothing extraordinary, but learners might think there is some kind of magic involved. What I mean is, if I teach you using a development board, you will eventually reach a point where you want to build your own product. Obviously, we can't use development boards for product creation, so you must be able to work with the microcontroller independently in your project. If you learn using a development board, when it comes to product design, you might be hesitant or scared to design the circuit using a standalone microcontroller. That's why in this tutorial, I'm going to teach you how to work with a standalone microcontroller. I'll be mounting one of these microcontrollers onto a breakout board so I can connect it to the breadboard. This way, I'll have full access to all the pins of the microcontroller. If you can set up a microcontroller this way, you will have no problem or fear when it comes to designing your own product. Alright, let's not waste time and get started with setting up the STM32 microcontroller and the steps for completing this project. Generally, microcontroller-based projects follow a few steps and we are going to go through all of them together here. First, we need to select the appropriate microcontroller based on our criteria. Then we'll write a program that will generate an executable file commonly known as a hex file, which can run on the microcontroller. After that, we'll need to set up the necessary hardware requirements, such as the power supply, connecting a crystal if needed, and so on. Finally, we'll use a programmer and its software to transfer the hex file to the microcontroller's memory. If everything is done correctly, the project will work, and there is nothing surprising about that. Now, let's move on to the first step. Step number 1, selecting the right microcontroller. The first step is selecting the right microcontroller for the project, one that has the necessary capabilities and isn't too expensive. I'm skipping this step in this video because setting up a blinking LED is not a big deal. Any microcontroller can handle it, so it doesn't really matter which one we use for this project. However, in this video, I'll be using the STM32F030K6T6 microcontroller. The reason is that I already have this microcontroller in my workshop, and its package and pin count are suitable for mounting it onto a breakout board for breadboard use. Some packages either can't be mounted on a breakout board, or if they can, they won't fit on a breadboard. For instance, some chips that are mounted on this breakout board can't be installed on a breadboard anymore. So the bottom line is you can use any microcontroller you have on hand for this project. Step number 2, writing program. The next step is writing a program for the microcontroller to generate the hex file. In the final step, we will transfer the hex file to the microcontroller's flash memory using a programmer device. To write the program and generate the hex file, we need a compiler. There are many compilers available, such as Kale, Microvision, or IAR, or STM32CubeIDE. You can use whichever compiler you prefer. Each one has its own pros and cons. I used to work with Kale, but since STM32CubeIDE was introduced, I switched to STM32CubeIDE. In this video, I'll be using STM32CubeIDE because it's newer, developed by ST, the company that makes STM32 microcontrollers. It's free, no need to buy a license, and it eliminates the need for any additional software. Note that other compilers can also work independently without extra software. For example, you can use Kale or IAR to write code for STM32 microcontrollers without additional software, but it's much harder that way because you have to manually configure all the settings by programming the registers directly, which is really complicated. Many of us are used to using intermediate software to handle the initial setup of microcontrollers. For example, when coding for AVR microcontrollers in CodeVision AVR, we used a tool called CodeWizard, which simplifies things. There is a similar tool for STM32 microcontrollers offered as a standalone software called STM32CubeMX, which helps you set up configurations and deliver a ready project for compilers like Kale or IAR. Just to be clear, STM32CubeMX is different from STM32CubeIDE. The former handles initial settings only, while the later handles settings and serves as a full compiler, allowing you to edit codes and compile it. If you want to use a compiler other than STM32CubeIDE, you will need STM32CubeMX as well. But I recommend using STM32CubeIDE because it provides an all-in-one solution. Now let's dive into STM32CubeIDE to see how to create a project, set up configurations, write the code, and finally generate the hex file. You can download STM32CubeIDE using the link provided in the description of the video. After downloading and installing this free software, open it, hover over the file menu, select new, and then click on STM32 project. This will open a window where you can select the desired microcontroller. This window also has another option, like if you are using a development board, you can select your board from the board selector tab, and all the relevant settings will be chosen for you. You can find almost any board here. As I mentioned earlier, we are going to write a program directly for a standalone microcontroller. So we'll go to MCU MPU selector tab and search for our microcontroller. In the commercial part number field, we'll type in our microcontroller's name, select it from the list and click next. In the new window that opens, we'll give our project a name and click finish. Now we wait for the project to be created. Once the project is created and you see a visual representation of the microcontroller, you are ready to configure it. As you can see, 5 of the pins are marked in a yellowish cream color and 2 pins are in olive green. The rest of the pins are gray. The gray pins are general purpose input-output pins for the microcontroller, and we can configure any of them as output to control an LED. For example, here I am using pin number 9 labeled PA3 as the output pin to turn the LED on and off. To define this pin as output, I click on the pin and select the GPIO output option. Now you can see that the pin has turned green, and next to it, it says GPIO output, which means that the pin has been successfully configured as an output. By the way, there are some special pins here. The VDD pin, which are pins 1 and 17, supply power to the microcontroller, and we need to connect them to 3.3 volts. Be sure to connect both pins 1 and 17 to the power supply. Similarly, the VSS pin serves as ground, and we should connect them to 0 volts. Again, both VSS pins need to be connected to ground. There are also a pin called VDDA, which supplies power to the analog to digital converter unit. If you are using the ADC unit, you should connect this pin to the power supply as well. In this project, we are not using the ADC, so we don't need to connect this pin to the power supply. The 2 olive-colored pins are boot 0 and NRSD. Boot 0 is used to select the boot mode of the microcontroller. For more detailed information, you can refer to the IC datasheet. I'll just mention that for this project, we are connecting the boot 0 pin to ground so that the microcontroller boots from the flash memory where we'll upload our program. I promise, in 99% of projects, you'll need to connect the boot 0 pin to ground. The NRSD pin is used to reset the microcontroller. It's active low, meaning that when it's connected to ground, the microcontroller will reset, and when it's connected to the power supply, the microcontroller will operate normally. Typically, we use a 10 kilo ohm resistor to pull up the reset pin, and we also connect it to a button so that we can reset the microcontroller by pressing the button whenever necessary. All right. Let's move on to the rest of settings. The first crucial setting is to click on Sys in the System Core section and enable the debug serial wire. When you do this, pin 23 and 24 are activated and turn green. You'll see the labels like Sys SWCLK and Sys SWDIO next to these pins. These are the programmer pins used to upload our program to the microcontroller. These 2 pins are enabled by default by the factory, so if you don't activate this option, the microcontroller will be programmed at the first time, but on the subsequent attempts, you won't be able to reprogram it because the pins weren't enabled. So make sure to check this box to avoid issues later on. The next setting is in the RCC section, which is for configuring the microcontroller's clock frequency. If you want to use an external crystal for your microcontroller, you need to set the high-speed clock to crystal ceramic resonator. More settings related to crystal and clock frequency can be found in the clock configuration section. You will see that the input frequency is set to 8 MHz, meaning that we need to connect an 8 MHz crystal to the microcontroller. When you enable an external crystal, pins 2 and 3 labeled RCC OSC in and RCC OSC out will be activated, and we'll need to connect the crystal to these pins. One important note is that if you are testing your microcontroller on a breadboard, I recommend not using a very high clock frequency because it could cause the microcontroller to hang. Even though this microcontroller can run at up to 48 MHz, if you are working on a breadboard, I suggest setting the clock frequency to no more than 16 MHz due to technical limitation on breadboards. Anyway, at this point, we don't need to make any more settings, and we can start writing code. To enter the coding environment and have all our configurations automatically turned into code, we'll go to the project menu and select build all. I'll do that now and click yes, and again click yes to generate the project. Now you can see that a default code has been generated. Be sure that any code you write is placed between a begin and end markers. Of course, you can write your code anywhere, but if it is not within these sections, any changes to the configurations will cause your code to be deleted, and only the code between begin and end will remain. For example, you can write your code here between these begin and end markers, or here, so that it won't be deleted later on. There's a specific reason for that, but I won't get into that in this video. Just know that your code should always be between begin and end markers. Now, let's scroll down to the main function of the program. Here it is. Inside this function, you'll find the main program loop. I mean the infinite while loop here. Since I want the LED to blink infinitely in this project, I write my code inside the main loop so that it repeats continuously. Notice that the main loop has two begin and end sections. This is the first one and this is the second one. It doesn't matter which section you choose to write your code in. I write mine in the first one. To make the LED blink, I need 4 lines of code. The first line to turn the LED on, the second line to add a half-second delay, and third line to turn the LED off, and fourth line to add another half-second delay. I'm using the HAL GPIO write pin function to control the LED. This function takes 3 parameters. The first parameter specifies the port name. Next, we are using pin 3 from port A, which is labeled as PA3. Even though this pin is pin 9 of the IC, it is pin 3 of port A. We are only concerned with the port name and pin number, not the IC pin number. In the first parameter, we define the port name by passing GPIO to refer the port A. In the second, we define the pin number 3 by passing GPIO underline pin underline 3. And in the third, we define the logic level. If the third parameter is GPIO underline pin underline set, the pin will output 3.3 volts, and if it is GPIO underline pin underline reset, the pin will output 0 volts. That's it, we have written the code. Now we need to convert this code into an executable file. If we go to project menu and click build all, the project will be compiled and the output files will be generated. If there are any errors in the code, they will be shown in the console tab. As you can see, there are no errors or warnings, so everything is correct. If we go to the project folder, we should see the output files created by the compiler. To do this, right-click on the project in the Project Explorer window, select Show In, and then choose System Explorer to open the project's location. Now, if we navigate the project folder and open the debug folder, we should find a file with the .hex extension. But as you can see, there isn't one. That's because the compiler hasn't been set to generate a hex file by default. We can easily change this by adjusting a setting to make sure the compiler generates a hex file as an output. To do this, go to the project menu, open the properties section, and in the C++ build section, select settings. Now in the MCU post-build output section, check the box for convert to Intel hex file and click apply and close. By doing this, the compiler will know that we need a hex file, and from now on, it will always generate one for this project. You only need to do this once per project. Now that we have made the necessary settings, we'll go back to the project menu and click build all again to rebuild the project and regenerate the output files. If we go back to the debug folder, we should now see the hex file, which is the executable file we'll transfer to the microcontroller's flash memory. We have now reached the final step, which is using a programmer to transfer the executable file to the microcontroller's flash memory. To do this, we need to connect the programmer to the microcontroller. To connect the programmer to the microcontroller, we'll need 4 wires. one ground wire to connect the programmer ground to the microcontroller's ground, a wire to connect the reset signal from the programmer to the reset pin on the microcontroller, and the other two wires to connect the SWCLK and SWDIO signals from the programmer to the relevant pins on the microcontroller, which are the pins 23 and 24. I'll make these connections and also connect the circuit's power supply. Now, to transfer the file onto the microcontroller, we'll need the programmer's software as well. There are many options for this, but I prefer using ST-Link utility software. It's free and you can download it from the link I placed in the description of this video. To program the microcontroller, I open the ST-Link utility software, go to the File menu, select Open, and in the window that opens, I locate and select the hex file and click Open. Now the contents of the file are displayed. To program the microcontroller, I can simply click the Program Verify button here. If everything was done correctly, the microcontroller should be programmed and the LED should immediately start blinking. If it doesn't, you may need to reset the microcontroller by manually pressing the reset button. As you can see, the microcontroller has been programmed and the LED is blinking. If you have reached this stage and your LED is blinking too, congratulations, you have successfully entered the amazing world of STM32 microcontrollers. This is a big achievement, and from now on, you can easily improve your skills with STM32 microcontrollers. You just need to work on more projects and study further in this field. But now, if you happen to be one of the unlucky ones getting programmer errors at this stage, I should say that these errors can have different causes, but most of them are related to the circuit, hardware, or connections in the project. For example, the power supply voltage might not be correct, or the connection between the microcontroller and the programmer might not be correctly made, or similar issues. You will need to try to identify the cause of error and fix it. I'm sure you will succeed. Alright friends, we have completed this project, our first project for entering the world of STM32 microcontrollers, and we did it successfully. Moving forward, I'll teach more STM32 based projects in this channel, and watching this video is a prerequisite for those. Anyway, thanks for watching. Please like this video, subscribe to my channel, and hit the notification bell so you don't miss out on the next videos. We have got some awesome projects and cool tutorials coming up. Until the next video, take care of yourself. Have a good one.